Okay, so hello and welcome everybody. Thank you for registering for the Endless Form Seminar Series hosted by the Cambridge University Biological Anthropology Society, an independent student-led society dedicated to origins research. We offer a warm welcome to our guest speakers today, Dr. Vincent Fernandez and Dr. Camille Berruyer. Vincent Fernandez is a paleontologist and beamline scientist on the BM-18 at the European Synchrotron Radiation Facility in the Structure of Materials Department. Among his many publications, he recently was part of a project with Roger Benson in which they described the anatomy of a stem lizard. Dr. Berruyer is an archaeozoologist and a current postdoc at University College London. Among her many publications, she was the co-author on the 2017 Nature paper by Dr. Isaiah Nengo, where they described an infant cranium belonging to a new species of Nyanzapithecine. I'll now hand the time over to Dr. Fernandez and Dr. Berruyer, and we kindly ask that all questions or comments be saved for the Q&A at the end.
Thank you. So, thanks everyone for coming, and thanks for having me for this seminar. Sharing screen. Let's go. All right. So, yes, thank you for having us today. So, we were introduced, so I'm Vincent. I'm going to talk about the work we are doing at the European Synchrotron, and where we're using the beamline to scan objects of the natural and cultural heritage world. And so Camille is a postdoc at UCL, but actually with us on site at the ESRF, and she's been with us for a few years now, and she will be handling the part of archaeozoology. So I will start the presentation, and she will take the second part. All right, so what is it that we do? What we do is tomography, and tomography means making a slice. So before doing X-ray tomography, I had a geological background, and the first time I heard about tomography was seismic tomography, and so that people using seismic waves to reconstruct the layers and the inner and basically the inner of Earth. So I was really confused of what's the link between like a CT scanner and that. Well, both are making slices, and there are many ways to make a slice and drawing what you see in that slice. So you could slice something physically, like this saucisson. You take your knife and you take a picture, or you make a drawing, and you can do that. And you can do that with a fossil, and it has been done for decades. So this is a therapsid from South Africa, and they have lots of these tiny therapsid skulls. So they were not afraid of like grinding. Actually, here it wasn't slicing, it was grinding. So they were just grinding a little bit of the fossil, drawing what they saw, grinding another 30 micron, drawing what they saw, and so on and so forth, which is something a bit brutal, one may think. But first, I mean, if you gain some information and you have other similar fossils, you can think, why not? Well, especially like back in the 60s, where X-ray computed tomography was not a thing. So, but it's still, people are still doing it now. Like when they have like many times the same specimen, and they don't hesitate to just like grind and take picture if other techniques are failing. This one is usually a technique like brutal, but it works. So, but when you have that, because it's the 21st century, and we can try to digitize even something like this. So I have a colleague in South Africa who actually like scan like with a photocopy scanner, like he scanned the drawing, and sorry. And this is like, so when like to go back, so when they were doing the slices, they were making like this wax products, but the wax model, they usually don't last very long. They are not super precise. So, but yeah, my colleague Julien Benoit and Sandra Jasinowski in South Africa, they scanned the paper, they imported all the information into a computer, they segmented the bones as we do when we deal with X-ray computed tomography, and actually managed to 3D print the specimen. So now we have another way to get a model. It's not, it looks a bit jagged. That's because like it was hand drawn when the thing was published. So it's like, it's not, we'll never get something perfect from something that was hand drawn, but yeah, that's what we can do. But that's not what we do with Camille. So what we do is a derivative of computed tomography. So the thing you have at the hospital, invented in the, invented in the 70s, and then developed first for medical use. Then it was developed for industry and biology and everywhere. And now basically you have these machines everywhere. And before I was at the ESRF, I was actually working at the Natural History Museum in London, and I was in charge of this machine. So, which is like the industrial equivalent of the medical CT scanner that I was showing before. And in this machine, you put something on the turntable, you have an X-ray source, it shines a conical beam, and bam, you have a radiograph. And so what happens? So the concept is you have an object that turns, and from this, all this radiograph, you load everything into a computer, and then you can apply some color, you can manipulate it in 3D, you can peel off some parts if you want, you can open it like without having to physically open the real object, and then you can really manipulate all the tiny parts that were like inside. So if you have like a very, very valuable object like this Kinder egg, and you don't want to open it because you don't like chocolate, you don't want to have chocolate on your egg, but you really want the toy, well, technology make it possible so that you can do that now. So, but we are not using this kind of machine. We are working at the European Synchrotron. So it's like a particle accelerator. And the main purposes of this particle accelerator is to produce X-rays. We are actually in this building here. So it's a very long beamline. It's for scanning large objects. And so that's the synchrotron view from the top. And the way it works is we have a bunch of electrons, first accelerated linearly, in a linear accelerator, so they call it a LINAC. And then it goes into a booster, so the speed, you increase the energy or you increase the speed, one or the other, they are linked. And when you have your electron going at the speed you want, you inject them into the storage ring. And everywhere in this storage ring, you have devices that make the electron generate X-rays. And so you collect the X-rays in the beamline. So the electrons, they are affected by magnets. The light isn't. So when the light is produced, it just goes straight. So that's why the beamlines are plugged tangentially to the synchrotron. So that's where we are. We are here in Ghana, right there. There are synchrotron orbits everywhere. There are a couple. So it says there are 3 in France, but it's actually 2 now. The CERN is not a synchrotron. It's like, this gets confused, but that's something like, so the one you see in Switzerland, it's actually in Zurich. And otherwise in the UK, you have one in Oxfordshire. So it's at Harwell, at the Harwell campus. You have the, what is it? Diamond, the Diamond light source. So, but yeah, they are a bit everywhere. And what we do with this, well, we scan fossils and tons and other things that are not fossils. And the big question is, I mean, it's like a big thing that looks like it's an instrument for physicists more than for paleontologists or archaeologists. But well, yeah, so why do we scan, why is it a good idea to use a synchrotron light source for, especially like why, it's not the question I should have asked, like why do paleontologists or archaeologists come to this facility to scan their stuff, especially if there is an instrument at the Natural History Museum, for instance, like these machines are everywhere. So what's the gain? Well, the gain, if I have to pinpoint one thing, is called phase contrast microtomography. And it works, it's very easy to understand the gain when we look at these 100 million year old pieces of amber. So these pieces of amber, they are completely opaque. So they are not like the shiny translucent one where you can make nice objects in them, like jewels and everything. So these ones are completely opaque, but we know from broken parts that they have lots of inclusions in them. So when you try to put one of these things into an X-ray source, usually it looks like this. So that's what we call absorption-based radiography. So like it's the classic phenomenon. You put something into an X-ray beam. It's depending on the density, you attenuate more or less. So that's why when you put your arm or limb or sort of like you don't see the soft tissue because they are not very dense, and you see the bones because they are denser. So you see the density variation basically. But in the case of amber with inclusion, usually the density variation is very small, if there is any, and so you end up seeing nothing. So this is just a radiograph. But what happens when you can use phase contrast, you can turn your image from this to that, and like suddenly you realize that, like from the previous one, you could have guessed that there was something there, but like suddenly it's like, oh yeah, sure, there is something there, but there was something there too as well. It's like it becomes crystal clear. So I'm not going to go into the detail, but the how, mostly because it's a bit of quantum mechanics. It doesn't really make sense. But what is happening is that you can see this dark and white fringes surrounding any time you will have something that doesn't have the same reflective index, you will have an interference pattern, so these dark and white edges. So basically it's highlighting any phases, like in the sense of mineral phases. And so if you do the full process and you scan all these blocks one by one, and you pinpoint like an insect of your, like an inclusion of your choosing, because it's not only insect. So like then you do the full scanning, like we did with the Kinder egg. Like then you load all the slides on your computer, and you can scroll through them and start recognizing structure. This is the body. These are the legs, and then you can actually do the most useful part. Is actually what we call segmentation. It's isolating the part of it that you think is interesting, and only view that. And from that you can make so you can keep it as a volume, or you can make a movie, you can make all your figures, you can actually make a mesh that represents the part that you segmented, and you can 3D print it. So it's very, very convenient, especially when you have an object that you want to describe, because these are insects that are 100 million years old. They were all new species of insects or any inclusions, and they had to be described. So that's one of the first one that was described. So like it's half a damselfly, poor thing. We also have a coleoptera and larva. So if you look at the scale, like these things are really, really tiny. It's basically 0.5 millimeter, like or about 1 millimeter in length. This is a slightly like a juvenile beetle. We can see the it's not really called the wings, but like the part covering the wings is not fully formed yet. And they've discovered a lot of things like plants, arachnids, gastropods, what have you, lots of things. So it's it works very well for ambers with inclusion, but basically it works with everything that has little density variation. So that's why paleontologists like to go to the synchrotron, because when you have a fossil, you have most of the cases little density variation. So that's what another case was the project I had the chance to work on for my PhD. I have to study these tiny little fossil eggs from the early Cretaceous of Thailand, and it's kind of the same story. So this one, so they're about like 2 centimeters in height maximum, and it's the same story. So when we do like a conventional macrotomography, it means we're using one of the instruments like the one at the NHM, like a laboratory system. So when we scan it with a machine like that, you get something like this. And you can kind of guess that there is something there. So this is a slice. So one of the things. It's not a radiograph with like the pieces of it. When we bring the same thing to the synchrotron, it gets like this. If we still use absorption synchrotron microtomography, if we still use only the absorption phenomenon, we get a clearer image because the synchrotron produces, I think it's 10 to the power 14 more photon than like a lab source. So it's like, yeah, like hundreds of billions more photons. So you have more signal, so you get better data because you have a lot more signal coming in. So it's clearer, but it's not changing the game. Like it's more or less the same information that you get. And when you do phase contrast tomography, that's where you start seeing things that were completely invisible with just the absorption. And then you can see that you have bones everywhere. So we did that in 3D to convince people that it was actually useful to do that. So in Salillon is where we did with the conventional laboratory system. This is the absorption-based synchrotron, which gives more result because it's a clearer signal, and this is the propagation phase contrast. And the bones are much better defined, and we can see a lot more of them. So it's like undoubtedly something that really is revolutionizing the study of fossils. And well, yeah, with numbers. So in the first one, we had like 21 bones. The second one, we had like 70, and this one, like 300 pieces of bone. It's not that this animal had 300 bone. It's more like it's 300 pieces. So for example, like some of the ribs are broken, and I can't know exactly which one should match with the other one. So sometimes it will count as 2. Also, the vertebrae is separated in 3 pieces. So here you have a centrum, and basically you have the neural arc that is separated in 2. So you have one here. It's difficult to see. This is also one. So like a vertebra is basically 3 bone. So that's why like even in a tiny portion of the eggs, you ended up like with lots of bones, but it's like parts of bone, I should have said. So I did the complete segmentation of 2 of the best eggs. So the colors are the part of the skeleton. So in yellow, it's the vertebral column. In red, it's the skull. Gray, it's the ribs, and blue, limbs. And green, it was the pectoral and pelvic girdle. And with that, we can manipulate our bones in 3D. So because we didn't have one complete embryo, we took the best bone from the 2 best eggs, and when we had missing bones, we made mirror versions of them to have a better representation of the final skeleton. And we ended up discovering the first lizard embryo preserved in an egg from the fossil record. So it was something quite exciting. But so I wanted to, well, I like this one. It's my PhD project. It's something really that I will cherish forever. But then I read the abstract again, and I said I was going to show dinosaur eggs. Funny story, when I started my PhD program, like we thought like these tiny eggs were dinosaurs, but yeah, they weren't. But I ended up working on dinosaurs eventually. So recently I worked with a team of people, mostly from Argentina, and we were working on, we had eggs from that are like about 200 million years old from Argentina. So with Diego Poland collaborator. So these eggs are about the size of a chicken egg. And they are very spherical and a bit flattened, probably because we know that they were a bit soft. So we scanned 30 of them, and but they have hundreds of them. We scanned 30 of them, and we discovered 3 embryos. And so the first task is to try to understand which species it is. So we try to identify a bone. So this is the dentary. And on this side, we actually have a lot of different animals. So we have a neonate, like a really hatchling, and we have so this is a juvenile, this is an adult, and so we have a complete series of these species on the site. And it's quite interesting because first, it's always interesting to see how a skeleton is evolving in a 200-million-year-old species, because it's not every time that you get to see that. I mean, fossilization is like a very rare phenomenon. So to actually get several individuals of a single species is something quite rare. And sometimes you don't realize immediately that these are different age. So you think these are different species. But anyway, so here we are sure we have like from embryo to adult, so we can see how the bones change, how they ossify. We have a lot of information. And what is quite interesting as well is like we have this big nest, and we have lots of them. So in these sedimentary horizons, we will have like a few nests, and then a few layers above, we have another nest, and a few layers above, we have another series of nests. So it means that these dinosaurs, they were just coming back to the same locality years after years to lay their eggs. So it's like many animals are doing that today. So it's normal that some dinosaurs were doing it as well. But it's a rare occasion when you can actually say which species was actually doing it. So like this site is just the beginning of a treasure trove of information. So certainly more information to come in the future about these dinosaurs. Another dinosaur, which is more or less one of the biggest things we have scanned so far. So this one is from South Africa. It's called Heterodontosaurus. It's about the size of a turkey. So it says it's 1.5 meter long, but you have with the tail, you get like it gives a false sense of the size, but at least for me, like when I see 1.5 meter, I imagine something very long. And when it's telling, when I got told that's about the size of a turkey, I was like, ah. But yeah, if you add a very long tail to a turkey, you get 1.5 meter. Anyhow, so this dinosaur was found into a seasonal river, so it was dry in summer, and but then it's actually in winter. In winter, it's dry. Sorry. So it's in South Africa. It gets very dry in winter, so the water level goes down, and they saw the bones. And we know that when the rainy seasons come, it's going to flood. The river will go up again, and it's going to damage the bone. So that's why when they came back, you can see that the digging site is all very squarish. It's because they use like a rock saw. Like people imagine like paleontologists just playing around with brushes. Well, we actually use big tools when we have to. And so we extract this dinosaur. Well, I haven't taken part of it. So the people in South Africa, they extracted it, and the team. This is Jonas Schwanier, Kimberly Chappell, and Kathleen Dolman. They all came with the dinosaur in their hand luggage, and we scanned it at the synchrotron. And luckily enough, because it was cut into tiny parts, we were able to scan the blocks individually, and then we can just reassemble everything and segment this complete dinosaur. If they hadn't cut it like that, when it would have been discovered, it would not have been possible to scan the whole thing at once, just for technical reasons. And so we had Victor Rademarker, who was a master student at the time, and he focused first on the thorax of this animal. So we have the vertebral column, the dorsal ribs in green, left arm and shoulder, the left leg, the pelvis, and the yellow things, which are abdominal ribs, and the purple things are sternal ribs. And it's very interesting because this dinosaur, Heterodontosaurus, it's quite old for a dinosaur, and it's the same lineage that eventually gave rise to Triceratops and Stegosaurus. So well, it's that kind of dinosaur. So it's not a theropod, like the Tyrannosaurus Rex and everything. It's not a sauropod. It's the other ones. And so in these groups, it's the first time that we discover a dinosaur with abdominal ribs, like this gastralia. And why is it a big deal to have gastralia in a dinosaur? Well, it's because when you look at modern relative of dinosaurs, so crocodiles and mostly birds, you can see that these animals have a very different way of breathing. So crocodile, they will have a slightly mobile chest, but mostly they have muscle attached to the gastralia, and they have muscle attached to their pelvis that will basically pull the viscera, and as well, like they will do an abdominal breathing, and that's how they make room for the air to come in. Birds, they do something completely different. They have air sacs everywhere, and they basically pump the air in and out, and so the air circulates into their lungs with air sacs. When you have air sacs, it's visible in your skeleton because the air sacs, they take some room. So like in this sauropod dinosaur, we have there is lots of pneumatization in the vertebral column. So it's because they are very close relative to birds, it's highly likely that they were using the same mechanism. But again, like Heterodontosaurus, it's a non-Niscan dinosaur. They don't have postcranial skeletal pneumaticity. So they were definitely not breathing like this. So that's what Victor Rademacher did. Like he looked at all the bones and looked at them in detail and did like a nice reconstruction and compare it with other animals. So this is Heterodontosaurus. So we have a very mobile chest because so we can see the joint between the sternal ribs and this paddle-like shaped sternal ribs, and then the dorsal ribs. And then we have the gastralia. So there is a lot of mobility in this dinosaur. If we look at more derived ornithischian dinosaurs, so Taliscosaurus, we have a very blunt joint between the sternal plate and the sternal ribs. So very little movement, and same between the dorsal ribs and the sternal ribs. It's very blunt. So they had a very stiff sternum. And then look at like birds, they have a bit of mobility in their ribs, but that's not really what they use a bit more. So then, because the pelvis is important for crocodiles, he also spent some time looking at the pelvis. What he saw is that, so he was looking at this. It's called the anterior pelvic process, which is abbreviated APE. So, and he normalized he's basically looking at the prominence of the process, because when you have a prominence on a bone, it means that the muscle attachment is more important. So if you have a little process for muscle attachment, it means the muscle is not very strong. The larger the process gets, the more it indicates how strong the muscle is. So that's what he's looking at. He's looking at the length of the entire pelvic process, and he sees that it's actually really small in Heterodontosaurus. So you see it's very basal dinosaur from this lineage, and basically it gets blue. So in that length scale of color map, it means it's getting longer. So it's getting longer, and so it means that through evolution in ornithischian, we have a muscle that starts to develop in this dinosaur. And then he's looking at the ischium, the length of the pubic rod, and here it's more or less the opposite. So it's very long in Heterodontosaurus and some basal ornithischian, but it's getting smaller through evolution. So with all this information, the story that came out is that it's probably all linked with the way they were breathing. So like stem dinosauromorph, like Silosaurus, it's probably a corossal ventilation as a mean of air exchange. So it means using a lot the abdominal ribs, the gastralia. When we arrive to Heterodontosaurus, we have the pubic is retroverted, so it's pointing backward, and so you reduce the usage of the efficiency of this colossal ventilation, but the rib cage is still very mobile. So it's probably still the mean way of changing the volume of the air in your lungs. And you have an incipient anterior pelvic process, so it's probably it shows already that there is a muscle that was attached to the pelvis. When we move to a more derived ornithischian scan like Telescosaurus, so we don't have gastralia with this, and we have lots of like nicely preserved ornithischian. So we know that, and we know no gastralia in any derived ornithischian. So we are quite sure that it was completely lost at some point. But so if you don't have gastralia, you can't do the colossal, I don't know why I put this word because I can't say it properly. like the abdominal breathing, basically. Long pubic rod is still long pubic rod, so it means there is room for muscle attachment. So maybe there was like a complete body wall deformation, like an abdominal movement, but just with the muscle attached to the pubic. It's a bit difficult to say. It's actually there. What we see is that the sternal ribs are very simplified, so there is less movement in the rib cage. So meaning they were using less and less the rib cage as a mean to change the volume of air. And basically the entire pelvic process is getting larger. So that's getting more prominent as a mean of air volume change. And so when we look something at Corythosaurus, we see that there is no movement, and like the sternum is very stiff, the pubic rod is really short, and the entire pelvic process is really enlarged. So like this, basically, Heterodontosaurus was the missing part of the puzzle to understand what happened from a basal stage to our derived ornithischian. So that was a nice project, and I hope it's going to be we get more information as well. Now that we throw this idea and it seems to make sense, we'll see if more information supports that. Well, that's basically everything that I said. I will just go very quickly. I thought I just mentioned that, but I don't want to. I want to leave some time to Camille to talk. So I'm just I wanted to talk about something that was a bit more recent. So with people from UCL, from Oxford, and the Oxford University Museum of Natural History. So I was invited to work on a project so it's from the Isle of Skye. It's actually that part of the Isle of Skye. And if you see here, there is a paleontologist on this beach looking for pieces of rocks like that. And this doesn't look much, but when we scanned that, there was a complete lizard in this tiny block. And it doesn't look extraordinary just like that, but there was like a lot of information. So, and it's a very old lizard. It's actually, and so we had like the skull is a bit scattered, but we have like the jaws and everything, and we can see it on both sides. We have like tiny bones, very well preserved, like the tiny bones of the limbs. And so I invite you to look at the scale bar. This is 5 millimeters, so it means like the diameter of this bone is a fraction of a millimeter. Like these bones are extremely small, so it's extraordinary that all of this preserved as it is, like in connection. And the interest of this specimen is that it's actually not a lizard; it's a stem lizard. It's a stem squamate, and we don't have a lot of these, and we actually don't have a lot of complete specimen like that. So this one is showing a lot of numerous features from the crown group, so your proper squamate, especially some stuff related to cranial kinesis. So the fact that they can disjoint their bone, and like especially snake, they have a very elevated cranial kinesis, so they can completely disjoint their bone and swallow much bigger prey that they should be able to. So this is something very important, and they already have like the they already show traits pointing towards disability, but they also preserve some features that were more ancestral. So it's an interesting. It's quite nice to have something that actually shows the state of stem lizard this early in the diversification of this group. And that's basically, I just wanted to mention that to show you some. It was published like just a couple of weeks ago, so you can look for it. There will be lots of images and stuff like that. And on that, I will just end the last part of the talk to Camille, who is gonna steal the screen sharing.
Thank you. So. Yes. Oh, sorry. Okay, so you should see the good presentation. Vincent, can you? Yeah, nice.
All good.
Thank you very much, Vincent, for this presentation. It was really nice, actually. I learned many things that I should have known. I'm really happy to be here today. So, as it was mentioned, my name is Camille Berruyer. I'm now a postdoc from the UCL, but I have done my PhD at the ESRF. My subject was on animal mummification in ancient Egypt. I wanted to speak today about a really specific mummy, so I will not go into detail on my PhD, so I just made a really, really tiny introduction. So, as you may know, Egyptian gods were linked to a specific animal species. It existed mummified animal, but the ones I will speak about today is the votive mummies. So they are votive offering that you can offer to a god, but you will offer it to a dedicated god. For example, you can offer cats to Bastet, dogs to Anubis, or crocodiles to Sobek. I have scanned more than 50 mummies, crocodile mummies actually, because it was really the main focus of my PhD. And I want today to show you a really specific one. So it's a mummy which came from the Musée des Confluences in Lyon. It's actually the largest animal collection outside Egypt. So it was really convenient to have this not far from the synchrotron. So this mummy is a bit particular because, as you can see, it's really damaged. We don't have any bandages, it's broken, and you can see that there is a kind of an abundant balm layer just surrounding the mummy. So most of the mummies are like this because they really suffered during time, because they were really not really the main focus of studies, but they would just bring back by peoples and after given to museums. So they're more or less all look like this, but this one is really particular. So we have scanned it. So usually we scan things to be able to see inside, but in this time it was really convenient to be able to rematch the two pieces of the mummy, so we can say that it's actually the same crocodile. That was the first point which were important. So now we can just remove the bone to see what is inside. So we can see that there is a crocodile. We can see the skin, but the first impression was a bit weird because we cannot see the feet and the arms of the crocodiles. It's a bit folded, it's a bit strange. And we can see that there is actually, sorry, I was showing with my fingers, doesn't work. There is a kind of an opening here. So if you go deeper, and if you continue to have a look inside the crocodile, we figured out that there is nothing inside. It's just a skin. Everything was removed, muscles, skeleton, organs, except the bones, which you cannot remove without damaging the skin. So the fingers, the skeleton, and the osteoderms, sorry. we see that inside the arms of that crocodile, it was filled with plants. And thanks to the microtomography, we are able to make really fine scans inside the crocodile. So we can zoom in to see some of the seeds that were inside these things that they put in it, just to kind of have a shape for this crocodile skin. We also was able to see the cut marks. This is a whole subject in archaeology, and it's something like I really like. I don't know why. It's just typically the marks that the ancient Egyptian left on the bones when they cut it. So it was really interesting to see it, because with the shape and the deeps of the marks, you can have an idea about the tool that were used. So for this, it was a sharp knife. It was not like a saw, but it was sharp knife, and it was more used by hitting it, more like doing this movement. And we also found these kind of traces in the skull, sorry. So with all this information, we tried to see, okay, why they did this. It was really a good question, but how they did it. So I tried it myself. So I had a crocodile to do experimentation. So I firstly have to remove everything inside without damaging too much the skin. As you can see, I just allow myself to put 2 more incisions here and there, because it's actually not crocodile, it's a caiman, and caiman have osteoderms in their this side. So it was the skin is a bit harder than crocodile. So I just allow me to do that. After, I had to place some vegetable inside the arms and the lips, just to try to have this kind of weird shape that we have. We fold it, and at this time, I realized that I had to put a rope on it, because as you can see here, I have to hand it with my own hands. So at the end, I just put a rope to be able to take a picture. And this fact is actually interesting. So if you compare the one that I've experimentally done and the one that we have scanned, it's quite the same. So we are happy to see that, well, it works. But the thing is that it took me 6 hours to do this. And it's something a bit weird, because just a bit of more context, I think it's important. Votive offering was a massive production. Ancient Egyptian produced millions of animal mummies. So we think that 6 hours to process a body was a bit strange, but okay. We go back to the datas. Inside the skull, we have found an interesting thing, which is here. This is an insect which is stuck on a membrane inside the skull of the crocodile. So here, here is a fresh one, when you can see that actually this membrane. So here it's the places where we found these insects, and thanks to the segmentation and also the fact that we can zoom in, we were able to see that this particular insect was a Dermest maculatus, which is a necrophagous insect that came in decaying cadaver. It's one of the latest insects that came in a dead body. So it was interesting, because this insect was actually dried as the crocodile was, and it was stuck on the membrane. So this insect came before the mummification. It was important to say that, because with all this information, we were able to kind of reconstruct what happens. First, we found back a rope, which it was used to maintain the crocodile. And I actually found it after the experimentation. It was really nice to see that. So the conclusion is that ancient Egyptian found a decaying cadaver. A crocodile died for several weeks. I think was really disgusting. And they processed the body to make it suitable for mummification. So they open it, they remove everything and continue to turn wrong in this crocodile. They dry it with the use of natron, with this, it's a mineral salt. After this, they put some balm in it. It's really often, we usually find balm in votive offering. They, after, kind of re-give a shape to this strange crocodile. They don't want him to have it really flat. It has to look like a crocodile. And after it was mummified in the sense that we can hear it. I mean, with linen bandages and things like this. We can see some of these linen bandages left here, so we know that it was more processed than just this. So the biggest conclusion of this is it was a mummy from a decaying cadaver. So they did something that was time-consuming and disgusting. It was lots of work to process this body. So for me, it's just the perfect illustration of the great importance of this religious practice in ancient Egypt. It was more valuable for them to spend time to create this thing than just threw away that crocodile to let it rot. And that's it.
Oh, great. Thank you so much for that, Dr. Fernandez and Dr. Berruyer. I see, the endless applications that the synchrotron has for both paleontology and archaeology, especially when you mentioned cut marks. Cut marks are very important for biological anthropologists. And now, there's so much that can be done and so much to do with this. And now we'll go ahead and open the floor up for questions. And if you don't mind, I have a question first. So I know you mentioned, I guess the synchrotron is limited, the size of things you can scan to how big the actual scanning chamber is. But is there a size limit for how small things can be to scan them? Because I know you showed the lizard, or the stem lizards, some of its bones were, they were millimetric, the measurement. So how much detail is lost, when things get to be that small, or is it lost?
So yeah, just so to answer first the other part, so when we the biggest thing we can scan is like we just said, like the new beamline where we are both working is, it's not fully finished yet, but the aim is to be able to scan something the size of a human body. So that's going to be the largest object we will be about, something like a very big, tall human, because it can do like 2.5 meters tall. The lizard that we scanned it with a resolution of 4 micron, which is definitely not the maximum we can do. Like on our beamline, we can do down to 0.7, or so, just about submicron. And so when you scan something submicron, like at 0.7, you usually have a field of view of like a millimeter or two. But that's on our beamline. On our neighbor beamline, they can go a little bit higher resolution. They can go 170 nanometer. So then the field of view is, it's about a third of a millimeter, so 300 micron. But then there is like a proper nanotomography beamline, and they can really go down to a few nanometer in resolution, and their objects are just like a few hundred, like a 100 micron or 50 micron. So that's more or less how small we can go.
Wow, thank you. And so we'll open it up if anyone can raise their hand or unmute themselves and ask questions. Yep, Pam?
Yeah. So, hi, I'm Pam Woodard from Washington University, and thank you very much for inviting me just to listen to this. This is fascinating. So I'm a radiologist by training. And so, it seems to me that, the advantages of the synchrotron for imaging above medical imaging are, not only the resolution, but also the exceptionally high energy. When you have fossils, with medical imaging, you're imaging soft tissues, and the densest things that we end up imaging are bones and metal, which you end up, often getting like beam hardening artifact off of metal. But with the with the samples that you're imaging, some of them are the rock essentially, or nacron, which would be rather dense. So I would guess that the synchrotron is really, of significant benefit for some of these very dense objects that you're trying to look at in detail. Would that be correct?
Yeah. No, it's true. It's like a synchrotron is not really made for really high energy. So, but that's what we aim for. So, like the new beamline, a synchrotron is usually made for a very small beam, and they usually have like a relatively low energy because they want to scan very small objects, so they don't need very high energy. But we've always been pushing on the other side, like to get a bigger beam and get higher energy. And the maximum we can do at the moment is 250 kilo electron volt.
Mm-hmm.
So it means we can go through 40, 50 centimeters of rock.
Or scan really dense things. So for example, we have scanned an archaeological pieces wrapped in gold, which it's not really easy to scan. So we scan this. And if I can mention, I am now working in a biomedical project on that beamline. And the really big advantage we have, you mentioned it because it's really not dense things. We are using HIP-CT, which is a kind of a protocol that we made that make us able to scan a complete organ down to the cellular level without cutting things, which is, I have learned this, a bit interesting for medicines and for medical research. So it's another application of this beamline.
Fascinating. Thank you.
Great. And do we have any more questions? Great. So if not, thank you, Dr. Fernandez and Dr. Berruyer, for joining us today. It's really fascinating. And we look forward to working with you both academically and as a society. And just to note for next week, on Friday, November 11th, we have Carol Ward, Professor Carol Ward, for The Shape of Human Evolution. And once again, we thank you for joining us today. So see you next week.
Thank you for having us. Bye.
Bye-bye.